Good evening to one and all. Is the video clear? And my voice also? Please tell. Thank you. So, any questions over the previous class? What we discussed? Do you have any? So, I want to start with the previous concept where we ended our session. There we discussed that whenever you have a cyclic group generated with an element A, while finding the other generators of the group, we follow a standard result that A power m is a generator of G if and only if GCD of m comma n equal to 1, where n is nothing but order of the element A. This is the result what we discussed, right? Any queries over that to anyone? Are you clear over this result? So in today's topic, I want to discuss about the concept of class equation and problems based on class equation. Prior to that, I want to take some problems for discussion. Then we have to go with a small concept called as silo theorems. So earlier it seems to be somewhat difficult following silo theorems. So I want to postpone this topic for some days. So after discussing with the problems and class equation, I want to start the second module, that is ring theory. So once we finish up with ring theory, then we come back for silo theorems and we do some problems based on this. The main use of silo theorems is nothing but whenever you know the order of a group, you can say the nature of the group and as well as the elements and its subgroups. That is the advantage of silo theorems. Suppose if I have mentioned that order of a group is 30, then immediately without knowing what are the elements in that group and what is the operation for that group, you can say that is it an abelian group or not, how many subgroups we can find, what could be the possible order of the elements in that, is it a cyclic group or not, and how many normal subgroups you are going to calculate for that group G that you are going to mention by simply knowing the order of the group. So that is the advantage of silo theorems. Okay. So we will discuss this part at the end, because while doing this we have to solve some previous year problems also. That's why we discuss this part at the end. Clear for all? So that could be the upcoming module for the sessions. You please take a note of it. Right. Now, as we know, if G is a cyclic group and G is isomorphic to another group G dash, then what happens? It is also becomes cyclic. And here, if A is the generator, here the generator is nothing but f of A, where f is nothing but an isomorphism from G to G dash. This is one interesting thing that we can observe. Let me say, suppose if we have taken the groups like G and G dash, and A is the generator for it, obviously f of A will be here. As you have taken that f is an isomorphism between these two. So if you take any element x belongs to G, then corresponding f of x will belong to G dash. Since G is generated by A, you can write x equal to A power n for some integer n. So if you apply f of x, it is nothing but f of A power n equals to f of A dot so on A n times, which gives that as f is a homomorphism, applying the condition of homomorphism, you can write it as f of A dot so on f of A n times, which is nothing but f of A whole power n. So here you can observe that if you take the value f of x, it is nothing but the power of f of A. So whatever the value you take image, it is nothing but f of A power something. So f of A is nothing but the generator of the group G dash. Clear? So if A is the generator on the left hand side, corresponding image is the generator on the right hand side. That we need to understand. You just take a note of it. Another observation we can make is, if you take a finite group of composite order, then we can say that it has a proper subgroup. The proof is not necessary here, but we are going to make use of this statement while proving the other problems. So whenever you take a finite group of composite order, then it will possess a proper subgroup. You just take a note of this. Right? And using that result, we can prove or we can solve one small problem. So let us consider a group G of order PQ, where P comma Q are distinct primes. So whenever a concept is given like this, Based on this, we can say that whatever the subgroup you take, or you can say every subgroup of G is cyclic. If you want to add a small thing, every proper subgroup of G is cyclic. So that we can understand. If you take a group G of order PQ, where P and Q are distinct primes, then we can say that if you consider any proper subgroup of G, it is always cyclic. That was the situation, right? The result is, or the proof of the result is very simple. If you say that H is a proper subgroup of G, so immediately for every subgroup we can apply the Lagrange's theorem. So order of H divides order of the group. So order of H must divide PQ, because we have taken that the group order is nothing but PQ. So from this, order of H must be either 1 or P or Q. It cannot be PQ because you have taken a proper subgroup. So H is not equal to the whole group G. So if you consider that order of H equal to 1, it means that H contains only one element, that is nothing but the trivial group identity. Since it contains only one element, it is by default a cyclic group. If you take that order of H equal to P, since P is a prime number, we have taken a small result that a group of prime order is cyclic. So this implies by known result H is cyclic. It is also true for the other case that if order of H is equal to Q, then also we can say that H is cyclic. So whatever the proper subgroup you consider, it becomes cyclic because it is having the prime order. Okay? Did you get that idea? So you take a note of that. Because we have taken proper subgroup. Yes, I am saying that this case we won't consider. This case we won't consider. So even though if you consider this case, it is also cyclic. That is what I am saying. Because it contains only one element, identity. So the case must be H order, if you consider, must be less than 1 and less than PQ. That's it. So if anybody has any doubt that if H is equal to singleton element E, is it cyclic or not? That is my answer. It is a cyclic because it contains only one element. Okay. So I am talking about the proper subgroups. So this case won't happen, even though if you consider, then for that situation, actually we need to understand one more thing, that I have mentioned that order of H is equal to 1. So by default, H contains only identity element. Since we are checking for the divisors of order of G, so what could be the possible divisors of order of G? I am checking. So while checking, this case will happen. This is also one possibility, but we don't take into consideration because it is a trivial subgroup apart from proper subgroup, right? Right. So let me take some other problems. Yeah. So generally one question comes that how many homomorphisms will exist? That is also a question. So for that, if you take two groups G and G dash, and they are finite groups by default, if you know their orders, say order of G is M, order of G dash is N, then the number of homomorphisms which will exist between these two is GCD of M comma N. That you take a note of it. The number of homomorphisms exists between the two groups is GCD of their orders. Now let us take one problem that find all homomorphisms from Z by 4Z to Z by 6Z. Let us discuss this problem so that you can have an idea how to construct a homomorphism between the sets that we can discuss. Right? You take a note of this problem. So just now I mentioned that if you consider the denominator values 4Z and 6Z, you have the values 4 and 6 here. So if you want to know how many such homomorphisms will exist, is nothing but GCD of 4 comma 6 that equal to 2. Now let us verify manually how to construct the homomorphisms between them. Right? So what could be the pattern of elements here in Z by 4Z? It is a quotient group, it is also a quotient group, right? What is the pattern of elements here in Z by 4Z? All the elements will be of the form set of all 4Z plus N, where N belongs to Z. Because whenever you write the groups with Z, the operation is by default plus. Because Z comma dot is not a group. Z comma plus is a group, since we are dealing with integers, right? So here, if we have the elements of the form 6Z plus N such that N belongs to Z. So here we need to understand that if you want to pair the respective sets in order to get a homomorphism, so you need to pair the elements of the form 4Z plus N of the form like 6Z plus N, a suitable form like this. Okay, and what could be the value of N here? That is also a question. Now let us say that whenever you consider the element of the form f of 4Z plus N, it is nothing but N into f of 4Z plus 1. Do you accept? This is nothing but this thing. Because if you consider 4z plus n, it is nothing but 4z plus 1 plus 1 plus so on plus 1 n times. So if you apply the property of homomorphism, it will become n into 4z plus 1, 4z plus 1, 4z plus 1 so on n times. Nothing but n into 4z plus 1. Okay? As per quotient multiplication, it will come like this. So, if you want to pair the element 4z plus n, you should take what is the possible pairing I can do for the value 4z plus n. Because every element here is nothing but n into this. So if you know the pairing pattern for this element, then you have done the pairing pattern for this value. So in other words, how many possible choices are there for pairing 4z plus 1? If you know, the same number of possible choices will occur for this element also, because this is written in terms of this. Accepted. Are you getting the idea or not? Say. Yeah. I will say like this. Suppose if you consider the line, so on. Suppose here we can say that each element in Z is a multiple of 1. Accepted? Right. So, if we know how to pair 1, since every number is a multiple of 1, automatically you know what could be the corresponding images for those elements. If you know the exact image of 1. Accepted? That is actually I am trying to say here. Whatever the value 4z plus n you take, it is nothing but a multiple of 4z plus 1. N into this thing will come. So if you know the image of 4z plus 1, automatically you can know the image of 4z plus n. Clear now? All of you. Right. Then at this point, we need to recollect one property, that order of f of a divides order of a. This thing we have mentioned as a small result earlier. Can you recollect that? Right. So here, four z plus n is nothing but the element a. Here the element will be f of a. Similarly, if you take 4z plus 1, it is f of 4z plus 1. Now the question is, what is the order of 4z plus 1? So for this, you need to understand that how many times you apply the operation plus for 4z plus 1, you will get the identity in this. So if you take a quotient ring G by H, the identity is nothing but H. So here the identity is 4z. So how many times if you add this element, you will get the value 4z. Say, What is the order of 4z plus 1 here? Four. Because if you add 4z plus 1 4 times, you will get 4z. Clear? Because you know h plus a plus h plus b is nothing but h plus a plus b. This is the form of cossets usually you will get. So if you add 4 times the same element, then only you will get the value as 4z. Accepted? Right. Now, as I have mentioned that order of f of a divides order of a. So, order of f of 4z plus 1 must divide 4, the order of this thing. Right? So, another thing is, from this perspective, what could be the divisors of 4 here? 1, 2, and 4. Right? So here we consider the values only 1 and 2, but not 4. Right? So you have to do the pairing in such a way that order of f of 4z plus 1 must be either 1 or 2, because order of f of a must divide order of a. So whatever the pairing you do, this element must has the order either 1 or 2. In other words, if you have taken a here, you can pair a with f of a such that this f of a must has order either 0 or 1. In such a way, you should pair the elements. Clear? The pattern, what we are going to say? Because since we are taking only homomorphism, not a monomorphism, we neglect 4. And not only this, it has other properties also. So we don't take the exact thing. So we take the divisors of 4 only. So we exclude the total value 4. Fine. And another thing is, so you have known one criteria that if you take the element 4z plus 1, its image is f of 4z plus 1, and it has possibility that either order of this element must be 1 or order of this element must be 2. The thing we have obtained so far as per the discussion is concerned. So whenever you take order 1, generally identity element will has the order 1. So in the right side group, what I mentioned, z by 6z, what is the identity element there? What is the identity element there in the right side set? Domain is z by 4z, codomain is z by 6z. So here the identity element is nothing but 4z, because understand that we are dealing with the cossets, not with the numbers. We are taking the cossets. So here the identity element is nothing but 6z. So if you want to pair the element, you are going to pair 4z plus 1 as the identity element, because order of this thing is nothing but 1, because we have taken the identity element pairing. So f of 4z plus 1 we write like this. So what is the possible homomorphism we are writing here? Whenever you take an element f of 4z plus n, it is equivalent to n into f of 4z plus 1, and this value is nothing but 6z. n into 6z is also nothing but 6z only. So this is nothing but 0 in the codomain. So whatever the element you take on the left hand side, you are simply pairing with the identity element there. That is one kind of homomorphism which we can have here. Okay? Clear? Are you getting the idea or not? How we are pairing the elements? So left side elements pattern will be like this. Its image is defined like this 6z. In a simple manner, I will say like this. All elements are paired with E dash. This is just like constant mapping. This is nothing but the constant homomorphism. We call it as the least homomorphism. Clear how the pairing is done here? Are you comfortable in getting the idea or not? Can I recap the thing again? I will say that. Just give me the moment. The whole idea for this problem is you are going to build a homomorphism between these two. Whatever the element here you take, it is nothing but of the form 4z plus n. So you need to calculate a formula such that by using that formula, applying for 4z plus n, the element here, you should know what could be the possible image on the right hand side. That is the whole idea. So for this, what I am saying, whatever the element 4z plus n you take on the left hand side, it is nothing but n into 4z plus 1. So if you want to know the image for this, it is better to know the image of this thing. So if you know the choices for this thing, you have automatically know the choices for this thing. So in order to specify a choice for this, we have used the result that order of f of a must divide order of a. So f of 4z plus 1 is this thing. This is a. And what is the order of this part? 4. So you can say that the value of f of 4z plus 1 is something such that this something order must be either 1 or 2. In other words, you can pair 4z plus 1 to any value in the codomain. You can pair 4z plus 1 to any value in the codomain. But whatever the value you are pairing here, this element must has order either 1 or 2. That is the whole idea behind it. So for this, if I have paired f of 4z plus 1 with 6z, since it is the identity element, its order is 1. So this is one kind of pairing between the two groups. Clear? Is it somewhat familiar now? To understand? Right. Just say, if you take the quotient group, the denominator is nothing but the identity. How it comes, if you have a doubt, I will tell. Just give me a moment. So, the, now tell me, what is the order of 6z there in the right hand side? So there you have struck it. I will tell again. See, if you take 4z plus 1 here, in this, it may be anything here. The image of 4z plus 1 is anything on the right hand side. So they're picking an element on the right hand side. I must be cautious that the element what I am taking must be having order either 1 or 2. So if you take the identity element on the right hand side, its order is 1. That's why I have paired 4z plus 1 with the value 6z. Clear now? That is the strategy. And whenever you take the quotient group, the denominator is nothing but the corresponding identity there. Does it make sense? Fine. So as our friends asked that, how 6z is identity? That's a small question. Now see. Say take the group G. You take any subgroup H for G. So what could be G by H? You are writing the respective cosets here. So 1H minus 1 into H, I into H, minus I into H. So among these things, one thing should be identity coset. It is nothing but 1H. Nothing but H. Because if you multiply any coset with this thing, the same value will come. Because 1 into H into minus 1 into H is nothing but 1 into minus 1 of H. What is the formula here? So this is nothing but minus 1 into H. So this acts as an identity element. And 1H is nothing but the subgroup itself. Similarly, if you take Z by 6Z, 6Z is nothing but the identity. Clear now? Right. So on the left hand side, don't misunderstand that 4Z plus 1 is a value. It is a coset. So this group consisting of cosets. On the right hand side, you have cosets. You are pairing one coset with the other coset. That is actually you are doing. So taking that 6Z as the image, it means that you are pairing every coset on the left hand side with the identity coset on the right hand side. That is the idea behind it. That's it. Don't feel that 4Z plus 1 is a number, it is a coset. So you are pairing a set with another set. So every coset on the left hand side is paired with the identity coset on the right hand side, which is nothing but 6Z. Okay? Fine. So you have done one kind of pairing here. So now let us go for another kind of pairing. So you can pair 4z plus 1 with anything such that its order must be 2. That is the other pairing possible for us here. So on the right hand side, if you start writing the cosets, so if you start writing the cosets on the right hand side, it is nothing but 0 plus 6z, 1 plus 6z, 2 plus 6z, 3 plus 6z, and so on. You can take the negative values also. Always these two are similar, so we can consider only positive things. There is no need to write the negative things. So z base 6z is nothing but this kind of cosets. So among these cosets, which coset has order 2? Which coset has order 2? Three plus 6z. Why? Because if you add this, since we have the formula, since it is a coset formed with multiples of 6, it contains all 6 multiples. 6z is nothing but since 6 is a part in it, 6 plus 6z is nothing but 6z. So 3 plus 6z you have added exactly 2 times. So the order of the element is nothing but 2. So how the pairing comes? F of 4z plus 1 is nothing but 6z plus 3. So this is the pairing you have taken. So these are the two possible homomorphisms between the given two groups. That was the conclusion of the problem. So if you want to know the pairing, what is f of 4z plus n? It is nothing but n into f of 4z plus 1, n into this is nothing but 6z plus 3, so nothing but 6z plus 3n. This is the pairing actually you are doing here. Clear? So these are the two homomorphisms available for the given groups. That is the solution of the problem. So on paper, we can simply mention the whole thing into just 5 lines. Can I write it? The whole summary of the problem? Right. So I will erase this. I will write the solution in a short manner. The whole summary of the problem is nothing but just these 5 lines. That's all. You take a note of that. After noting, you please inform. Is it clear for you, the whole discussion? Any queries for anybody on this? Those are the required 2 functions, how we are defining the homomorphisms. That's all. So how we are defining them like so? For this is the reason behind it. Now I want to take some definitions now, which will be interesting, and based on that, I want to take the 2 previous year problems, which are already asked earlier. I want to think about them so that we can have a conclusion for today's session, because this problem has taken much time for us. Now let us take the definition conjugate elements. Now you take a group G and take an element A belongs to G. So we say that an element B belongs to G is conjugate of A if there exist that's it. You take a note of that. So you can simply understand the fact that you have learned about similar matrices. Did you hear the word similar matrices in linear algebra and matrices? Say, have you heard? So in linear algebra, we take that if you take a square matrix A, we say that A is similar to another square matrix B, or B is similar to the square matrix A. If you are able to find a matrix P such that determinant of P is not equal to 0 and A is equal to P inverse BC, P inverse BP. This type of situation we calculate while doing eigenvalues and eigenvectors, where you have done the diagonalizability concept. Can you have the idea? So there we mentioned that P inverse AP is equal to D, we say that the matrix A is similar to the diagonal matrix D because we have calculated a new matrix P, which is a non-singular one from the eigenvalues and eigenvectors. Could you recollect the idea? So just like that, if you take a group, you take a value A and we say that another value B is similar to A if you can write A is equal to C inverse BC. And we say that A and B are conjugate elements. The main purpose of saying like this is, if you take the group G, you fix an element A and you calculate what are the elements which are conjugate to A. So this we call it as conjugacy class. So in other words, these conjugacy classes acts like cosets. So the whole group G is bifurcated into partitions. This is a conjugacy class, this is a conjugacy class, this is a conjugacy class, etc. So in a simple manner, in the group G, you are pairing those elements which are conjugate to a fixed value. You can just call it as a neighborhood in other regular words for understanding. So G is nothing but the union of conjugacy classes of A. This is the definition of conjugacy classes. So for a fixed element, you are pairing all the elements into one set which are conjugate to A. That set we are calling it as a conjugacy class. The impact on the group is, the whole group is nothing but union of these small sections. Okay? Clear? Right. And from this point of view, we define a formula that we call it as class equation. So if you take a group G, then order of the group is equal to order of the center plus order of the conjugacy classes. So in a simple manner, the diagram you can visualize it as, this is the whole group. This we can call it as center. And the remaining part is as bifurcated into conjugacy classes. So if you want to know the whole number of elements in group, it is nothing but number of elements in the center plus number of elements in the each class. Clear? The idea? This equation we call it as class equation. You please take a note of it. And there is a small result that how many elements in a conjugacy class you will have is equal to order of the group by order of the normalizer of A. This is a formula. You please take a note of this. For these results, we have a theoretical proof, but we are not interested in them because our interest is to solve some previous year questions based on this. Okay. So is it clear for everyone what is a conjugacy class, what is class equation, and how many elements will be there in a conjugacy class? Please tell. What is meant by a conjugacy class and what is meant by a class equation? See, total number of elements in the group order of G is equal to total number of elements in the center and number of elements outside the center. Clear? This is the actual thing. So this is center of the group. This is the remaining part of the group. So this remaining part is bifurcated into small sections, parts. So if you want to know the order of the remaining part, you know what is the order of each section, how many number of elements here, 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 and here, etc. So you are calculating the number of elements in the conjugacy classes, so which are outside the center. So A does not belong to the center. How many elements are there in the conjugacy class of A? And here, how many elements are there in the center? So order of the group is nothing but number of elements in the center plus number of elements outside the center. And outside the center is bifurcated into small parts. That is the whole idea. Fine. Everyone. If it is clear, now I am going to take the problem which is given in the previous problems. Shall I continue? Right. N of A is called normalizer. What is meant by normalizer? You are going to find the elements in the group which satisfy commutative property with only one element. So what is meant by center actually? In the whole group G, you take a part, we call it as center because whatever the element you take, this element satisfies commutative property with the entire group. This element satisfies commutative property with the entire group. And what is normalizer? If you take the group, you fix an element, you are collecting those elements in G which satisfy commutative property only with A. So always center of the group is a subset of normalizer. This is by default. Okay. So center is nothing but the elements which satisfy commutative property with the whole group. Normalizer means commutative property only with one element. So this is the smallest one, that is the larger one. Clear? And normalizer is a subset of G. This is the hierarchy if you want to know. Right. So can I take the problem now? Right. So today's class topics are somewhat little bit confusion for you because you are freshly learning some points and problems you are doing based on that. So here the problem is, if G is a group of order p power alpha or p power n, this is the problem. Please take a note of it. After noting, please tell. Say, have you noted that? Now just understand the concept. Suppose I have taken that order of G is equal to 4. So what it means, order of the group is 2 square. It is of the form p power alpha, say. Right. So if you calculate how many elements are there in the center, it must be always greater than 1. So at least 2 elements will be there in the center. That is the objective of the problem. Fine. Right. Now let us go to the solution for it. So you have the case that since a group is given, you don't know whether it is abelian or not abelian. So if the given group is abelian, means the whole group satisfies commutative property. So in this case, G and center both are equal, because this is exclusively commutative property satisfied elements. If the group is abelian, these two are nothing but same. Since you know that G contains p power n elements, so therefore order of the center is always greater than 1. Clear now the section? Are you getting the idea or not? Right. Now take the second case. G is not abelian. It means that G and center both are different. So if you talk about the hierarchy, so this is the hierarchy. Since these two are different, you can say that there exists an element in the group which does not belong to the center. So you can observe that this is a subgroup of G and it is also a subgroup of G. So by Lagrange's theorem, every subgroup divides the order of the group. So you can apply the property there. So you can say that order of n of A is equal to p power m. Since order of H divides order of G, the Lagrange's theorem concept I am applying here. So if you consider what is the order of conjugacy class, it is nothing but order of the group by order of the normalizer. So this is equal to p power n by p power m, p power n minus m. So this is nothing but it is a multiple of p. So if you take a conjugacy class, its order is p power n minus m. Okay? Is it fine for all of you? Any more questions for anybody? Always by default m less than n, because order of n of A is dividing order of G, right? It is by default. We need to assume that always m less than n. Fine. Now let us write the class equation here. So order of the group is equal to order of the center plus summation A does not belong to the center, order of the conjugacy class of A. This is the class equation. Accepted all? So please understand, if you take one conjugacy class, it is a multiple of P. So it is true for every conjugacy class. So every conjugacy class, if you consider how many elements are there, it is a multiple of P. So if you consider the multiples of P here, it is also a multiple of P. So here you can say that order of G is given by P power n. Order of Z we don't know. here Kp. Since order of conjugacy class is a multiple of P. So from this you can say that order of Z is equal to P power n minus Kp. So if you take common P, so it is also a multiple of P. Accepted? Now you have taken that P is a prime number. So what is the starting value for P then? 2. Because P is nothing but a prime number. Accepted? The starting value of P is 2. So you have calculated that order of Z means how many elements in the center are there. So the number of elements in the center is a multiple of P. So it is greater than 1. That is the solution of the problem. That's it. Now you got the idea how we have used the class equation here. So please take a note of it. So I want to take one more problem. It is also given in the previous year papers. Shall I continue? So please take a note of it. I will wait. So what is the conclusion? It is greater than 1 because it is a multiple of P, isn't it? That is our question task in the problem actually asked. We have to show that order of the center is greater than 1. Center contains more than one element. Since order of Z is equal to a multiple of P, P means minimum value is 2. Always it is greater than 1. Fine? Yeah. Can I take the other problem? Right. So the problem what we did states that if order of G is equal to P power n, then order of the center is greater than 1. This is the problem we have discussed just now. Clear to everyone? Now the current problem what we are going to take is a group of order P square is abelian. It is a previous year question we will discuss right now. It is also asked in the previous year papers. A group of order P square is abelian. Now the whole idea here is, since we have to show that it is abelian, there is no direct proof available for us. So let us go it in the opposite way. So let us assume that the group which is having order P square is not abelian. Then we start doing a process, we will get a contradiction. Therefore, our supposition must be wrong. Hence, we confirm that a group of order P square is abelian. Okay? The ideology? All of you. Right. Now, if possible, suppose order of G is equal to P square and G is not abelian. Let us take like that. Therefore, immediately we can say that G and center both are different. There exists an element in the group which does not belong to the center, and this is the hierarchy for us. So you can say that Z of G is strictly less than N of A, and this is strictly less than G. Please take a note of this. This is the hierarchy you have. Now we say that order of N of A divides order of G. So order of N of A must be either 1, P or P square. So it is P. 1 is not possible, P square is not possible because this is a proper subset of this. Clear to all? Are you getting the logic? The smallest set is center, bigger than this is normalizer, then bigger than this is the group G. So center is a subgroup of G and normalizer is also a subgroup of G. Since subgroup order divides group order, so order of N of A divides P square. The divisors of P square are nothing but 1 P square. Since it is a proper subgroup, its order cannot be 1. Since it is a smaller than G, its order cannot be P square. The only possibility is P for it. Okay? Right. Also, order of Z divides order of G because this is also a subgroup of G. So if you consider order of Z, it must be either 1, P or P square. Any one value should come here. Since these two are different, this case won't happen. In the previous result, whenever group order is of the form P power something, center contains more than one element. So this thing not possible. Therefore, order of Z is equal to P. Okay? Did you get the logic? All of you. Now please understand. This is obviously a smaller set compared to N of A. And you are saying that a smaller set and a larger set both will have the same order. Is it practically possible? This is a contradiction. So why this contradiction has come? Because we have taken that G is not abelian. Therefore, G must be abelian. That's all. Is the logic clear for everyone? For all, any questions? So you please take a note of this solution. So let us wind up our discussion here. In the next class, I want to start with the second module, that is ring theory. After going to some extent in ring theory, we will come back with groups. There we discuss the concept of silo theorems. Because in order to know the applicability of silo theorems in a better manner, You should have know all the definitions of subgroups, normal subgroups, properties, etc., etc. So it will take a small time for you to recollect all the results what you have learned. So you take a ample time and recollect all the results and practice them. And once you finish with some extent of rings, we come back to groups and we finish the small concept, that is silo theorems. Okay? In that case, it is same. In that case, that is same, right? If G is abelian, then order of G, Z of G, N of A, both are equal. That is the actual content of the problem. So the conclusion of the problem is how the conjunction is arrived here. You have proved that order of N of A is P. N of A contains exactly P elements. Order of Z contains P, means center contains exactly P elements. So here you are saying that this is a smaller set, this is a larger set. Smaller set and a larger set both have same number of elements, which is practically absurd. That is a contradiction. So the contradiction is arrived because in the beginning you have supposed that G is not an abelian group. So G must be abelian. That is the conclusion. Right? Fine. Then let us wind up our discussion here now. And if you want to add something, you can add. So that is for today. And from Monday onwards, we start the second module, that is ring theory. This will be interesting for you. So compared to group theory, ring theory has less number of concepts while discussing. So initially ring theory contains lot of definitions, but the logic is quite a simple. So if you understand the ideology of group theory, ring theory is just like a cakewalk for you. So any other questions for anybody here? Thank you, Dan.